Okay, so let's take a look at what we know about this sketch. We know this is a parabola opening up. Y-intercept is 3. Does it have any x-intercepts?
No.
No. So that means is it entirely above or entirely below the axis? Above. So this is going to be above the axis. Okay, and over here this is a line. Y-intercept is 0. So we've got everything we can get there, so now we need to find intersection points. So x squared plus 3 equals negative 2x. X squared plus 2x plus 3. We already figured out this does not factor. If this were a minus 3, it would factor. But at plus 3, it does not factor. So that means that what does it mean if there's no intersection point?
They don't intersect.
They don't intersect, right? So one curve is entirely above the other forever. So we just need to figure out which one it is. So over here, we know that x cubed comes through 3. So we know we have this. And that's pretty sloppy. It's okay. That's as much as you need. And then we know this is a line. It goes through here. And it has a negative slope. So does it matter if I got the slope exactly right? No, not really. Here, I'm just looking for from here to here. Okay, so this is 2. Did I do that right?
How did you get a 0 and 0 then for the line?
For this one, for the line? Well, you could write it as mx plus b. B is 0. Or you could put in x equals 0. You get y equals 0, either way.
Oh,
Okay, so I have a top and a bottom curve. Does it matter that this curve is below the x-axis? Do I need to do anything with that? The answer is no. If I'm just looking at area between curves, I'm going to take top curve, find it, minus the bottom curve. So can I do this all in one piece? Do the top and bottom curves ever switch places? No, it's always the same top curve. So what is our setup then? Our area is from 0 to 2, which is my top curve. Yeah, x squared plus 3 minus, I'm going to add a parenthesis here. For this one, we don't really have to have it, but a lot of times when we subtract, I think you should just be in a habit when you write subtract, open a parenthesis, because if you have more than one term, it's easy to lose minus signs if you don't have a reminder. And if you run out of, you can have small parentheses and big ones. You can also have square brackets. If you get really far into things, you can just be creative about how you specify those. Okay, so I'll leave you guys to work this out. All right, so now let's look at what happens if it's very similar, but not quite. So now let's look at this one. F of x is x squared minus 3, the same g of x, and the same. So what's the fundamental difference then? This right here shifts down. So now we're likely to have an intersection point that's going to matter. Okay, so let's go ahead and find that intersection point. X squared minus 3 minus 2x. Can you guys factor about that fast for this one? That's something that you should, at this point in your mathematical career, you should be working towards being able to go about that fast. Partly because you've seen this one before, partly because you know this is only a 3 and a 1. So it's got to be 3 and 1. One's positive, one's negative. The positive one is the bigger one to get the positive middle term. So that's something to be working toward. Okay, so we know that we have intersection points at x equals 1 and x equals negative 3. All right, so let's start graphing. The line still looks something like that. I gave it a little bit of a steep slope because it's negative 2, so a little bit steeper than 1 to 1. And then I know I have, it goes down here, goes through at negative 3. And x-intercepts, plus and minus square root of 3, so somewhere over here. Is that going to really matter as much? Do I need to worry about x-intercepts if I'm looking at area between two curves? That's not so important. Area between the curve and the x-axis definitely have to have the intercepts because they're like intersection points, but not as important here. So I know at x equals 1 and at x equals negative 3. I didn't quite get there. So does that seem about right? So it intersects here at 1 going to go through here about 1.7, so that seems sort of right. Okay, so what is my area of interest? So does everyone get a graph sort of like this? Do I really care what happens over here? No, because I'm really looking here, right? So this doesn't need to be perfection. I'm not worried about that. So now let's go ahead and put in, we have this line and this line. So I'm interested in an area just in here, just there, between the two curves. Hang on one moment. Hello? Hello? Yes. Yes. Okay. Yeah. Oh, that's
What did
normal.
you do? X squared minus locus negative 2x.
Yeah, no, he Brussels it.
What did you with the g of x to find where the intersection comes?
Yeah.
Can we do that?
Sorry.
Oh.
Those of you who are not parents yet, that was the middle school calling. Whenever the middle school calls in the middle of the day, you're like,
Yeah.
So, my youngest boy is prone to nosebleeds, so he got popped in the nose while playing basketball in gym and the torrent. I'm like, that's okay. He's good. It happens all the time. He's a wrestler. It happens all the time. Okay, so now we can get back to this. So sorry for that little extra interlude. All right, so now we're looking for area between curves. If it helps you, and you want to do the color-coded thing, or you want to do the solid line, go ahead and there are a lot of lines on here, and so it may be helpful to kind of re-put in the lines of interest. Because that shows you a little bit better where the area is. So I'm looking at this area here and this area here. They're two pieces. And there's a big old intersection point in the middle. So that's going to suggest to you that you're going to have two integrals because the top and bottom curves are going to change. So let's take a look. So you need to know where this intersection point is. So that's at 1. So I know from 0 to 1, so my area is some space. From 0 to 1, so what's the top curve?
Negative 2x.
Yes, the line. If it helps you, start literally, put your pen on the top curve and draw an arrow down to the bottom curve. So that helps you anchor which is which. The top curve is literally the one that is physically, vertically above the other one. So this would be negative 2x minus the bottom curve, which is obviously the other one. Again, keep your parentheses, extra set of parentheses. So that's this first area. The second area then is what? Yeah, so we're going to go from 1 to 2, that's this part, and the top curve is going to switch, right? So we're going to have x squared minus 3 minus negative 2x. And then we just crank that out. Okay. So the sketch is the important part for this, and I think that's actually the part that troubles people sometimes, is getting that quick sketch. So just remember, you're looking for the shape, x and y intercepts, and intersection points. And that's really all you need. It doesn't need to be any fancier than that. Okay? For the test, I will most likely, for last semester I did the same, I'll most likely just have you set up, get to this point and stop. I will test how well you know how to integrate in other problems. Once you get the setup, the rest of this is crunching through, but it's easy to feel like you're getting tangled in all of the numbers and subtractions and that's not really what I'm testing. So either I'll have you set them all up, or I may have you do one and not the other. Just set up one and do the other one all the way through. But, so there's that. Okay, so now let's look at. Is that okay? Any questions on that? Oh, but then there is one more piece. We can look at. Let's go back. Let's revisit this problem. One of the first ones we had, x squared minus 4, and where we go? We went from 0 to 3. Okay, so let's get this sketch back on. We've already done this. So here's 4, 4, 2, and so we're interested in this area. And so this area here, and this area here. And before, what we did is we said, well, we know that the integral down here will be negative, so we just throw a negative sign out front. That makes it positive for area. This one's already positive, good to go. You can also, if you want to do all of these problems in exactly the same way, we can treat this as an upper curve versus lower curve problem. So if I looked from 0 to 2, I have two curves. I have this curve, that's the x-axis, and I have this curve. Well, which one is the top curve? The x-axis. What is the equation of the x-axis? It has an equation.
0.
Yeah, y equals 0, right? It hasn't gone up, hasn't gone down. So I can write y equals 0, the top curve, minus the bottom curve. Right, that's the first part. And then I can do it again. Now I've got this curve and that one again. So now I can add from 2 to 3, top curve, minus bottom curve. And if you compare that to what we did before, it's exactly the same. When you take out the 0, right, you get that. And we take out this 0, that minus sign we just had in the front. So you can consider this either way. It totally is up to you. They both are exactly the same answer. They're really the same reasoning. It's just a difference in how you look at it. So either one's fine. Okay, so let's look at some word problems. Oh, and then the last thing is sometimes you'll say find the area bounded by two curves, and that's because they have two intersection points, and just the two curves alone are going to set up the whole area. So I'm going to let you look at that one later. All right, so now let's do an average value and a useful life. That will be perfect. And that should wrap us up. So average value. So if we know, I want to particularly look at cost. So this is average value. The average value of any function is the following. It's the area under the function divided by its width. So if you've got some function that's varying over a certain interval, if you look at the interval, right, you can figure out there's kind of an average value running through it. You can kind of figure out what that would be. This will give you that average value. All right, so let's look at this particular problem. This cost is the one that's kind of interesting. So let's look at, we have a cost function, 1,000 plus 10x. So I want you to find so a couple of things. Average cost per item for 20 of whatever these are. That's one thing. And then the other one is the average value of the cost function over 0 to 20. These are very different. This is the one we've been doing all semester. The average cost per item for 20 items. That means find your total cost for 20 items. This is C bar. We've been doing that one for a while. So remember how we find C bar. It's just whatever the cost function is divided by x. So what would it be for 20? Just plug in 20 everywhere, right? So 1,000 plus 200 divided by 20. 1,200 divided by 20, 60. It's a word problem, so it needs a word answer. So what do I need to? I need to add something to that.
Per item.
Yes, per item, and it's what per item? Let's go ahead and throw a dollar sign on it. Dollars per item. How do you know what the units are? This is dollars, and that is number of items. So it's right there, dollars per item. So that's the one we've been doing all semester. So, and how will you know? It will say the average cost per item. That's the important part, per item. This one's different. Average value of the cost function. This is an average total value. So if I'm making between 0 and 20 items, that cost is going to vary, right? In the beginning, it's only 1,000. And by the time I get to 20, it's 1,200. So my cost is changing. So what if I said, okay, fine. I know I'm going to make somewhere between, say, 200 and 500 of these items. On average, what should I expect for my cost? I can find an average total cost. So how do we do that? So the way you know what this one is it's the average value of the function. So it's an average total. So that's this one. So why don't you guys go ahead and set that up. And we'll look at that. Actually, so it was number 87.
Mm-hmm.
87?
Yes.
I'm just going to get set up for that. Okay. So we're interested 0 to 20 of the function, 1,000 plus 20x. And you'll notice on assignments, I'll sometimes put in parentheses and dx's. That's really the complete, just like you wouldn't say, if you were finding a derivative, you might say d dx. You would never just write d, right? That'd be kind of weird. d dx tells you what variable, so I keep putting that on. So here is, here's this part, and then you want to say divided by 20 minus 0, and then just crunch out those numbers. Okay, so per item is the C bar we've been doing for a while, and then average value of the function is an average total value. So which number is going to be bigger? The second one. The total cost is going to definitely be bigger than the per item cost. Yeah. So you expect a smaller number here and a bigger number here. Okay. All right. So now let's look at a useful life problem. We'll look at number 87 from what was due today. Round this up. So this one's useful life. If you need this one, I'll give you this one for the test. Useful life is defined as when the marginal cost is equal to the marginal revenue, where that is true. So it's a t value. So basically you're saying if it's costing, at some point it's costing more than the money, per item than the money you're making. So at that point, and this might be for something that has maintenance costs. So the maintenance costs are starting to, the marginal maintenance costs are starting to equal the marginal revenue. It's kind of like, you have an old car, and at some point you chuck the money into it, and you're like, okay, I've reached a point where this has become too much per year. That's marginal per year, and so I'm going to stop and just sell it for whatever I can get to get a new one. Okay, so here for number 87, it said an amusement company maintains records for each video game it installs in an arcade. Suppose that cost and revenue are what they normally are, and we know this. We know that C prime of t is 2, and we know that R prime of t is 9 e to the negative 0.3 t.
So is that information given?
Yeah, that's no problem. Yeah. So on this one, it just. So the one on this does not, yeah, you need to copy down what I'm writing now. This is number 87 from what was due today. So this is number 87 on page 390. Okay, so the question is, find the area between them over the interval from t equals 0 to the useful life. So I want to find the area between C prime and R prime from t equals 0 to whatever its useful life is. So the first thing we need to do is figure out what the useful life is. So we need to set these equal. So we're going to say 2 is equal to 9 e to the minus 0.3 t. Okay, so this, I know we haven't done a lot of this semester. This is pre-calc computation. So t is up in the exponent, so we need to start peeling back layers. The first thing we're going to do is divide by 9. Now I'm going to undo the exponential. I do that with a ln. So when we rewrite it, the exponential becomes the ln on the other side. So I'll get ln of 2/9 equals negative 0.3 t. And now I need to divide both sides by negative 0.3. ln of a number less than 1 is negative. So I've got a negative number equals negative times t. So t turns out to be positive, as we expect. So ln 2/9 over minus 0.3. Does anyone know? Remember, is it 5? Anyone remember what that was?
It comes out, yeah.
Pretty close to 5, I think. We're going to call it 5. I don't know. All right, so we're going to call it 5. 5 what? What are we in? T is in
Years.
All right, so we're going to call that 5 years. So that means now we need to come over here and find the area. So a sketch would be handy. We have two curves. C prime equals 2. What shape is that?
At 2, sure.
So horizontal line, T, right at 2. And what shape is this? This is an exponential.
It's like approaching 0.
Yeah, so let's think about this. So it's an exponential, it's decreasing, so it's going to look something like this. We just need to figure out where it goes through the y-axis. So it goes through the y-axis when t is 0. When t is 0, what is this? E to the 0 is 1. So at t equals 0, 9. So I'm going to draw this a little lower. Here's 2, and here's 9. And it's going here, and at some point they're going to cross, right? I just found that. They're going to cross at 5. I just found that. So let me see if I can fix that up a little bit. So right here at 5, they cross. So what am I interested in? From time equals 0 until I get to the end of the useful life. So here's time equals 0, and here's the useful life. So I'm interested in that area. So I need a top curve, bottom curve. Which one's the top curve?
Exponential.
Exponential, right? Exponential is the top, coming down to 2. So I'll have the integral from 0 to 5, 9 e to the minus 0.3t minus 2 dt. What will this represent? What is r prime minus c prime? Revenue minus cost is profit. So this is really p prime. So if I integrate, so really what I've done is I've said from 0 to 5, I've integrated p prime. So what am I going to get for an answer? It's going to be my total profit, right? This is going to end up being my profit at 5 minus my initial profit. So when you integrate a derivative, you get back to the original function. So really what this is saying is, what is my profit over the course of the useful life of this arcade game? That seems like a reasonable question to want to know the answer to. Okay. Any questions on that? What? So this we're just going to compute here. We just haven't done that part. So what time is it now?
9:13.
Okay. All right, let's work that out because this one is not in fact on the notes because I sort of didn't do that one yet. So let's actually work this one out so you'll have it. Okay, so this is actually a good example. Is this a basic or not?
No.
Sort of yes and no, right? This one's a basic, and this one's not. Treat them separately. So if you want to actually write separate integrals, so we can write 0 to 5. I'm going to pull that 9 out front. E to the minus 0.3t minus 2 dt. That's not a bad idea because I'm going to be messing with this one, and how I mess with this one does not affect that easy piece. Okay, so either in your head or on paper, separate them out. So this one's easy, that's just 2t. So what about this one? Is it a basic?
Not quite.
No, because it's not just an e to the t, it's an e to the something else. So the derivative here is negative 0.3. I don't have it, so I'm going to put it in and then divide it back out. Now I have this piece right here. Do I need to worry about that piece anymore? That's the derivative of the inside. That piece is gone. Let me come over here so I can write a little bigger. Okay, so what do I end up with then? So, what's 9 divided by negative 0.3? Somebody do that? 30? Negative 30? Okay, so negative 30, 0 to 5, negative 0.3, e to the negative 0.3t, minus, I'm just writing it out a little bit bigger, for the camera. Okay, so this piece right here derivative of the inside, so I don't need to worry about that. So negative 30, derivative, antiderivative of a E is itself. This comes over to be an evaluation bar, minus antiderivative of 2,
What? I mean,
2t, right, 2t, from 0 to 5. Now, if you want to, you could recombine them, if you wanted to, or you could just start plugging in. So negative 30 e to the minus 1.5. I'm going to do like this, negative 30, and then do this piece like this. So here, and then minus e to the 0. I think that's easier than trying to track that negative sign through multiple different things. And then minus 2 times t at 5 and t at 0. I think that's easier to pull. So if you've got a minus, if you've got a negative on the front, I would pull that out. All right, and so then you just crank through those numbers. So I'll let you crank through those. So, like I said, I'm here now today, and I'm here tomorrow, 11 to 12:15. I can come in a little bit earlier if you need me, and then after that, I will be answering everything by email. Oh, I have assignments to turn back. Let me do that.